Hello and welcome to another lecture of classical motion of a single particle. In this lecture, we also continue our previous discussion on the motion under a central force. So, let us assume the particle of mass m is moving under a force which has this specific form, and we call that a central force, and we know that this is a curless force, this is a conservative force field, the total mechanical energy is conserved. This is also a force field where the total torque vanishes, that is why the angular momentum is conserved, and since the angular momentum is conserved, we also showed that the motion is confined in a plane and that is why we just need r theta as the independent space variables, space coordinates actually. Then again we had another conclusion from the conservation of the momentum, angular momentum as well. We also said that r square theta dot is h, which is the angular momentum magnitude per unit mass, and this is constant, and that is why we actually can get rid of the theta dot as well from the equations of dynamics, and finally, the equation of dynamics becomes effectively one dimensional. Associating or involving only r or r dot or r double dots, okay, but not anything like, I mean, it does not need exclusively theta or theta dot, because whenever you get theta dot you can substitute that by h by r square. Okay. So, you just use that, theta dot is equal to h by r square. Then the equation of dynamics becomes equation of dynamics which is meaningful only in the radial direction, because the force is in the radial direction. It simply becomes m r double dot minus h square by r cube is equal to f of r. Okay. Now, we are simply saying this is the equation of dynamics under a central force. Okay. The cross radial component actually, so this is the radial component, radial part of equation of dynamics, and the cross radial part simply says r square theta dot is equal to h. Okay. So, this is the cross radial part. Now, I also showed that the velocity is given by this r dot r cap plus r theta dot theta cap, and A is given by this expression r double dot minus r theta dot square r cap, okay, plus 2 r dot theta dot plus r theta double dot theta cap. Okay. So, this is the I mean synopsis of what we have done till now on the central force. Okay. So, now we will actually continue our the discussion which we just started at the very end of the last lecture, that is to find the orbit. One can be interested to find the orbit, that is r as a function of theta or theta as a function of r. Before going to that, just let me clarify that if you have this, so this is a second order, once again I just write like this, second order ordinary differential equation, okay, in R, and hence knowing Fr, one should in principle solve to find R as a function of t and also R dot as a function of t. I said that once R is given, I mean R is obtained, then you know R square, okay. Then you can find h by R square, which is theta dot, and from that you also can find theta and theta, I mean then theta and theta dot are also known, okay. Now coming back to this point, that how to find the orbit. For that we said that we have to just always, whenever we have an equation like that, for example dr dt is equal to something, then we have to write dr dt is equal to dr d theta times d theta dt, and this d theta dt is theta dot, which is h by r square. If I regularly substitute this, then finally you will see that the purpose is solved, okay. Then I know d2r dt2 in the same way is nothing but d dt of this h by r square dr d theta, and then it will be d d theta h by r square dr d theta dt, which I can again write theta dot. Then I can write again, so this theta dot is nothing but h by r square. So, I can write this is h by r square h over r square d2r d theta 2 plus dr d theta, and then this thing, my d d theta of this thing is nothing but minus 2h by r cube dr d theta, okay. So, finally, you will have something like this h by r square d2r d theta 2 minus 2h by r cube, actually it should be correct, yes, 2h by r cube dr d theta whole square, okay. And so, finally, you can then write, recalling m r double dot minus r theta dot square is equal to f r, we can actually write m r double dot is the whole thing, this I can write this is, so h square by r to the 4 d2r d theta 2 minus 2h square by r to the 5 dr d theta whole square, okay, I think yes, then minus r, then theta dot square is nothing but h square by r to the 4. So, I have this equal to f of r. Then simply I can write finally that h square by r to the 4 d2r d theta 2 minus 2h square by r to the 5 dr d theta square minus h square by r cube is equal to f of r by m, okay. So, you see this is the equation, general equation for orbit, okay, general equation for orbit of orbit. So, if I now give you, if you are given r as a function of r theta, then you can find easily f of r. or if you are given f of r, then you have to solve for r. But you have to solve what? You have to solve a second order nonlinear ODE in r and theta, and which is not necessarily very easy to solve. Okay. So, the question is, can we actually do something more interesting so that things are easy? Okay. One possibility I am just telling you that this is not I mean useless in general. Okay. Maybe let us say I can have an orbit, let us say my orbit is like r is equal to k theta, for example. I do not know what this is, you just think about this type of orbit, but let us say my orbit is r is equal to k theta, k is a constant. Okay. Constant. Then I can easily say that what will be dr d theta, that is k, and what will be d2r d theta, 2, that will be 0. Okay. Then what will be, okay. Now orbit equation gives this. So, this term will be 0, this term will be simply k square. Okay. So, it will have minus 2h square k square by r to the 5 minus 2h square k square by r to the 5. You will also have minus h square by r cube by r cube. Okay. You see the expression is not bad, because here k has a dimension of length, because theta has dimensionless, this is an angle. So, you see that this is actually the dimension of like, so you have h square and k square and r to the 5, they will cancel to give you, I mean they will somehow partially cancel each other, okay, to give 1 by r cube, and this is also 1 by r cube. So, in that sense this is okay, and this is equal to your f of r by m. So, finally, what will be your law of force? The law, so the law of force is basically f r is equal to m times minus 2h square k square by r to the 5 minus h square by r cube. Okay. So, you see this is exactly what we get directly from this orbit equation. So, this is not a straightforward law of a single power law like f r is equal to some r to the power n. This is not like that. So, this is a composite power law. Okay. So, you can do that, but many a cases the problem occurs that when we give you the law of force you know, and you have to solve this equation. Okay. Then actually the business becomes very tough, because then you have to solve a second order non-linear equation with some square term in the first order derivative. Okay. Then there is a shortcut way, or I would say a little bit easier way out, which is nothing but to transform, to simplify the situation, of course comparatively. I am not saying that it will simplify enormously, comparatively. Okay. Situation, we substitute u is equal to 1 by r. Now, in this point there is a small subtlety you have to understand, that these two situations are not exactly equivalent, because whenever you have laws f of r, so the force laws are in as a function of r, then you see like you can have this type of force laws without any problem for all r possible. Let us say like some alpha r to the power, let us say n, where n is positive, okay, greater than 0, n greater than 0. And then when we say that if n is less than 0, then we know actually then r not equal to 0 is somehow required, because otherwise this thing will blow up, okay? And we do not want this type of situation. When you have u as your variable, then on the other hand you will have, for example, the same law, you will have a of r is equal to some alpha u to the power minus n, and that means alpha by u to the power n. And then the point is that this u should not go to 0. Okay. So, again the point is that when your n is negative, okay, then u should not go to 0. Okay. And when, of course, when n positive, that means a of u, I would say here u, yeah, a of u is equal to alpha u to the power n. So, then you will see that this part, okay, this part is, I mean, defined for all values, but you have to also understand this is meaningful, I mean meaningful when you write this is equal to alpha by r to the power n. So, apparently there is a conflict, okay, or I mean how to say, like, is a problem of consistency. That means that for n less than 0, I mean less than equal to 0, okay, you can have a I mean you have to exclude the 0 point here, but here when you have less than equal to n equal to 0, then you actually have to exclude u is equal to 0 here. Okay. But these two conditions are not equal, because n less than 0, okay, basically says that for r n greater than 0. Okay. So, this is something you have to just think and tell me that why, I mean is this a real problem in the whole formulation or what to. So, basically once again just to simplify the situation, to simplify what I am trying to convey is that when r is your variable, then you cannot go to r is equal to 0 in general, you have to exclude that. Okay. When u is your variable, then you cannot go to u is equal to infinity. Okay. That is the point. But let us say we do not know that, but it is also true that whenever u comes to the denominator, then is it okay to take u is equal to 0, although that will give me r is equal to infinity. Okay. So, what is the possible solution? So, in general, in order to first of all at this step, in order to get rid of all these problems, what we will do, we will actually think that whenever we will do u, so both u and r, they are well defined and none of them are actually blowing up. Okay. So, if you do, then you will see that things are actually, the orbit equation becomes very simplified. So, r double dot is equal to d dt of dr dt, and once again now you see this r dot is nothing but dr dt, which is dr d theta dt. So, instead of r, now I will write 1 over u. So, this will be d of 1 over u d theta times d theta dt, which is theta dot. Okay. Now, what is theta dot? Theta dot is h by r square, theta dot is equal to, but that is equal to h u square. Okay. So, I write that u square, and then d d theta of 1 over u is nothing but minus 1 over u square du d theta. So, it is actually minus du d theta, you see the simplification. Okay. So, many things actually can be solved by this thing. So, this theta is h u square. So, I would say there is a h which is missing over here, and then here there will be another h. So, I just write like properly minus h du d theta. Okay. And so, then this is nothing but d dt, I just go from this to this line, okay, d dt of h du d theta with a minus sign is equal to d d theta minus h du d theta d theta dt again. So, d theta dt is theta dot, which is nothing but h u square. Now, what is this? This has two terms. So, the first term is minus h d 2 u d theta 2, another is so d d theta of h, which is 0, because h is constant. So, this is can be as simple as that, and so dot h times u square. Okay. Now, I can simply write the simplified form of this equation over here. So, I finally have m r double dot minus r theta dot square, okay, is equal to f of r. So, now instead of that I can write m minus h square u square d 2 u d theta 2 minus r is 1 over u, I can write that, and theta dot square is nothing but h square u to the 4. This is equal to f of r, and then finally you will have d 2 u d theta 2 plus u, 1 u will go away actually from here. So, it will be u cube. So, u is equal to minus of f 1 by u, I am just writing r as 1 by u by m h square u square. Okay. This equation is of substantial interest in the case of central motion. Okay. And this equation is known as equation of Binet equation. Okay. Now, what is the difference between this equation and the equation what we get over here? So, you see, this is a second order differential equation, I understand, but this is much more easier to handle, because this part, okay, is linear in u, okay, but it was non-linear in case of r. Okay. And now, if I simply tell you to use this equation to find some very interesting trajectories, I mean if I actually tell you to find trajectories from force law and force laws from trajectory, you will see many cases you can solve without problem. So, for example, I am writing this equation d 2 u d theta 2 plus u is equal to minus f of 1 over u by m h square u square, and the first case is I am saying r cos theta is equal to constant k. This is constant. Okay. Then I know that if I have this, I can actually go, I can actually take something like this. Yeah, I can actually do a little bit easy, I start with a little bit easier one. So, yeah, I start with a little bit easier one, and you actually tell me why I am taking that. R sec theta is equal to k, okay, or maybe that will be, just a minute, let me just think. Yes, I think I would start with this one. Okay, I think I will start with this one. Yeah, okay. So, r cos theta is equal to some constant. Okay. So, what I can do is equal to r k sec theta. Okay, no problem in that. And then of course, if you write that, then you again say that u, which is nothing but 1 by r, is actually 1 by k sec theta. So, it is k prime cos theta. So, where k prime is nothing but 1 over k. I think this is much more easier. Yeah, you can also check the other one, okay, that is r sec theta is equal to constant. Okay. If you do that, then what will be du d theta? Then du d theta is equal to minus k prime sin theta, and d2u d theta 2 is equal to minus k prime cos theta. And hence, Binet equation gives minus k prime cos theta plus k prime cos theta is equal to minus f of 1 by u m h square u square. So, you see that will cancel each other, and you have the force has 0 magnitude. It means no force is there. Now, what is the meaning of that? That is, this is the case of a free particle. So, uniform velocity, okay. And now, who can tell me that what is the trajectory here? R cos theta. So, actually if you see in polar coordinate, if I say r cos theta is equal to constant, so this is, so the particle is moving in such a way that its r cos theta is constant. That means r cos theta is nothing but its x coordinate. So, this is r, this is theta, okay. So, and this is r maybe when the particle is here p. So, this is r cos theta, this part. So, x is equal to r cos theta. So, r cos theta k constant is actually equivalent to x is equal to constant. So, actually the particle is moving parallel to the y axis with some constant x, okay, and that is nothing but a straight line, and this is possible when this particle is subject to 0 force, okay. Now, I am also giving you some examples which are very, very interesting, that r is equal to e to the power minus theta, then u is equal to e to the power plus theta, because u is 1 by r, and then du d theta is equal to again e to the power theta, d2u d theta 2, d2u d theta 2 is also equal to e to the power theta, okay. So, if this is the case, Binet equation gives e to the power theta plus e to the power theta, okay, is equal to minus f 1 over u m h square u square. Now, what they are, e to the power thetas? They are nothing but, so if I write, so 2 theta, 2 e to the power theta. Now, what is e to the power theta? This is u itself. So, I write like this, minus f of 1 by u m h square u square, and that is why you will have f of 1 over u is equal to minus 2 m h square u cube is nothing but then f of r will be proportional to 1 by r cube. All these things are positive, then this is a minus sign. So, it will be actually 1 by r cube force law and attractive in nature. Okay. Now, I am going to another case. This is the last case for, to discuss in this lecture. So, that is r is equal to k theta to the power minus 1. That means r theta is actually equal to k. So, in an r theta plane, this will be given by a rectangular hyperbola. Okay. So, if you have such trajectory, then we have to find the force law. Okay. Here we are actually what we are doing, we are starting from a trajectory and we are finding the force law. We can actually do the inverse, which is a little bit trickier, and from case to case you have to really check whether you can do the integration smartly, by analytical processor or you have to do using numerical methods. Okay. So, if you have r theta is equal to k, then you can actually write u is equal to again k prime theta, the same thing. So, it was like k by theta. So, u will be theta by k. So, 1 by k prime is 1 by k prime is equal to actually k. And so, you have this. Now, du d theta is constant and d2u d theta 2 is equal to 0. And that is why finally, you again have Binet equation gives 0 plus u is equal to minus f of 1 by u m h square u square. Again you see your f is nothing but minus m h square u cube. So, f of r is equal to minus m h square by r cube. So, again you have a attractive inverse cube law. This is also attractive inverse cube law. Okay. Now, why I have discussed these two examples? Now, after seeing this Binet equation, maybe you have some impression in mind that if I give a law of force, then I will get the trajectory, or if I give a trajectory, then the law I get the law of force, and this trajectory to law of force mapping or the correspondence is actually 1 to 1. This example actually what I just discussed is actually trying to contradict that, and I mean this was used deliberately by me to make as a measure of caution to you that there is no hard and fast rule that you cannot have two different trajectories right directly from the same law of force. Okay. Maybe you can have an idea that you may have some temptation to think that if I give one type of central force law, then maybe I will have a unique type of trajectory. Actually, it is not. You see that starting from inverse cube law, you can actually reach e to the power theta, you can actually also reach this. Finally, you can also check that if you just do something like this, this is totally possible. Now, the question is why starting from the same type of force law we may have different trajectories. I mean, if you want to understand very simply, then this is nothing but due to the different type of constants, okay, of the force functions. So, for example, here the force function may be f is equal to some minus k1 by r cube, and here for example, this f is equal to some minus k2 by r cube. Okay. And what is the difference between them? Can you understand why these two things actually gives you different trajectories? Can you somehow relate that to some concepts of the constants of motion of some initial conditions? Okay. Just think about that, and we will try to continue in this direction in the next lecture. Okay. Thank you.